Okay, so I think then we can continue with our discussion of several more worked out problems.
Sure.
So now we are going to take a look at a problem related to portfolio optimization. So we have Kabir, and he is going to, let's say, invest rupees 1. In case you are thinking, why would anybody want to invest rupees 1? Let's think of like this can be 1 million or something. We are not specifying the units. It's just 1, right? For us. It's like, and you want to split it, or rather Kabir wants to split it between a safe royal deposit, which is giving this RF equal to 5%, and expected return is 12% and volatility is 20%, right? So again, we have kept the numbers here same as the video lectures, just to kind of like make things a bit simple, because then this will help to reinforce these things. But you will get to see different numbers in the problem set. So we are just making sure you have understood this basic material that was already there, right? So so with the risk aversion lambda, so this lambda, that parameter that we have, that is often called the risk aversion parameter, okay? Because this measures how much aversion there is to risk. Remember, higher the value of lambda, the more aversion to risk. Lower the value of lambda, less aversion to risk. So we have the mean variance utility function. So this is again something that hopefully you remember, or if not, you should look up the previous notes. And the important thing is all the expressions that we have written here, expected value of the portfolio, return from the portfolio, and the variance of return from portfolio, this can be expressed in terms of the parameters of the situation that we are given, right? So and the choice variable. So the expected return of the portfolio is the weight you are putting on the safe asset multiplied by the return from the safe asset, and the weight you are putting on the risky asset multiplied by the expected return from the risky asset, right? Variance, as we had mentioned, comes only from the risky asset, and that's going to correspond to W square sigma square B, and the weights must satisfy the sum up to 1, right? So as we discussed, they can solve it in two different ways analytically, and there's a way to solve it computationally also, but let's first focus on how to solve it analytically. So method 1, because this is a two asset problem, you can write one asset in terms of the other, right? And so we can express W as the weight that you are putting on the fleet, and then this ends up getting that W safe can be written as 1 minus W, right? Because remember, W safe plus W risky was 1. So then we can put this all back in the objective function, so as to write the objective function as a function of W only, right? So there is only one choice variable W, and we have managed to successfully write everything in terms of this, right? Again, in case this is not clear, if we just go up a bit, can we go up a bit? Not down, up. So I just want to spell out in case it was not clear from the lectures or something. So we have got this W safe is basically 1 minus W. You have got RF, which is a parameter. W risky is what we are calling W, right? So that's this expectation of ERP that we have basically written down here, okay? And this other term is, remember, W square sigma B square. So you have got this lambda by 2 times W square sigma B square, right? So that's how we get it. So again, simple problem. It's a concave quadratic, so we can just do the standard first order condition, set the derivative equal to 0. We have already discussed this in the video, but again, if this is something that is not clear, we encourage you to go back and take a look at it, and then you end up getting this expression that we had seen, right? And if you put in the numbers, this is what we get. Okay, so there is now this second method, which is the Lagrange multiplier, right? And here again, the first step is, as we discussed, you have to write the Lagrangian, and then you have to basically set the second step is to set the partial derivatives equal to 0. So you are going to get 3 partial derivatives corresponding to the 3 variables you have, W safe, W risky, and mu. And that will give you 3 first order conditions, right? All linear. So fairly easy to solve. And if you solve that, you end up getting with this expression for W risky, which is what the same that we had got before, right? So this is basically the exercise. Again, pretty straightforward if you have seen Lagrangian before. If not, then take this as an opportunity to actually learn about the Lagrangian, which is a very useful tool and which we'll be using again, and in fact generalizing later on in the course if we have enough time, right? So what does this chosen portfolio look like? If we go down, a bit. So basically, corresponding to W star equal to 0.4375, you can calculate what's going to be the expected return also, right? How do we do that? Because remember, this expected return from the portfolio was something we had expressed as a function of the two weights, which we have now calculated, and the return from the risky asset and the safe asset numbers which are given to you, right? So you can actually plug this in, and then you can do the calculations, and this is how you find out what's the expected return from the portfolio, right? Remember, this is something that you cannot find before you have done the problem, because you don't know what's the optimal way to put, right? So in order to calculate what's the at the optimal point, what's going to be the expected return from the portfolio, first step is you kind of like find out, you set up the problem, you solve it using one of the two methods, you get the optimal weight on the two assets, and then you put it back in the expected return from the portfolio. So similarly, now you can find out what's the standard deviation of the portfolio return. And notice that this is not the same thing as the variance, right? Remember, standard deviation is the square root of the variance. So this is the formula for the standard deviation, and you can also get this, right? So basically, if Kabir is optimizing given that objective function, this is the expected return and the volatility that she is going to get. And as you would have guessed, this is notice that this expected return 8%, 8.06% is something which is between the riskless 5% and the risky assets 12%, right? Because essentially Kabir has traded off the certainty that he was getting from the safe asset to invest more money in the risky asset, right? That's why the expected return has gone up. But this has not come for free, right? This has come from that there is now a cost that he is also exposed to risk, and he's exposed to basically this 8.75% standard deviation of return risk, right? Remember, he dislikes risk. So this is the other thing. Okay, the final thing that we covered in this course are about numerical tools, and Neela is basically helping out her friends here, and basically she's writing the program that the group is going to use. So we have already met the three people in the group, and two small numerical issues came up for Neela. So one was about how do you read a rate which is not of the curve, right? So remember, when we discussed this yield curve, we discussed this problem that sometimes you are going to have situations where you are going to get information about the rate corresponding to 3 years and the rate corresponding to 5 years. But you may need information about coupons that are coming out at 3.5 years, right? So how do you use the information that is available to you? Well, one way is to do linear interpolation. So geometrically, that is pretty clear how you would do it, right? You would connect the 3 and the 5 point, and then you would find out the point corresponding to 3.5, right? But algebraically, how do you do it? So this is basically the application of the formula that you had seen generally in the lecture. We basically want to find out the rate corresponding to 3.5, and we basically have the rate corresponding to 3, which is 6. Then you have to give a weightage to the difference, and this is what we get, right? So there is a easier way to write this. I leave it up to you, but this will give you the basically the same idea, and you end up getting 6.25%. Now, uh, even without writing the formula, you could have actually done this, right? How would you have done this? Basically, the way I think about it is that I want to find out what is the rate at 3.5 years, and I have information about 3 years and 5 years. So 3.5 is basically 25% of the way between 3 and 5, right? So basically the answer would be 25% of the way between 6 and 7, and so therefore 6.25, right? So I mean, even without doing the math, that's the beauty of linear interpolation, right? You don't really need to do the math here. You could just do it mentally as well, right? So there are fancier methods that Professor Shorish also mentioned in the lecture that again you can like look up in more advanced treatments, right? The other thing that she might have to do is she might have to find out the value at a particular point of a function, but she may not have the exact kind of like tools to compute the value of the function, right? So at that point, she would need to use approximations. Now, in the lecture, we had discussed exponentials, right? E to the power x. But sometimes we'll see that you might need to actually do log expansion as well, right? So just as we had kind of like worked with the general Taylor formula to get an expression for e to the power x, you can also do the same for log expression. And again, this is something that you might have seen in high school. So what is the expansion of log 1 plus x if you expand it around x equal to 0? So if you follow the same method that we outlined in the slides for e to the power x, you end up getting a formula which looks like this, right? So now suppose that Neela has to find out the value of this around 1.5, right? So what would be so then she has to take x equal to 0.5. So then log 1.5. Then you have to put in on the right hand side x equal to 0.5, x square will become 0.5 square by 2 and so on, right? So this is the cubic approximation and you end up getting a value of 0.4167, right? Now, if you actually look up the calculator and see what's going to be the approximation, this is around 0.4055. So this is roughly an error of 0.011. So by error, we mean the difference. So that's around 2.7%, right? Now, if you add in one more value, you are going to get a better approximation. So you end up getting 0.4011, which is closer. So the error rate is now less. And basically, each additional term you're doing, you are shrinking the gap. And the reason why you are doing it is because it's this factorial like structure, right? But there is a cost, of course, right? You have to do more computation. So the lesson that you take away is kind of practical, that near the expansion point, small number of terms is good enough to buy high accuracy. But if you're moving further away, then kind of like, you have to add more terms. And you should keep an eye on how fast the terms are shrinking, right? That will give you an idea of when to stop, right? So these are some things that we can just do using pen and paper, and you will be doing problems related to that. But a lot of these things we will probably want to do computationally also, right? So we'll be later on providing you with tools to kind of like also show you how to implement these things computationally. So Shorish, do you have any final comments before we log off this session on this worked out problems for the week? You're muted, Shorish.
No, Vikram, this is fantastic. I think this is just perfect place to end this session.
Right. And then hopefully now you can actually solve some of these problems yourself, and then you get the more confidence to move ahead to the next week.
Absolutely.